I was so confused at first.
Okay, so I'm gonna draw the picture. E to the x is a growth curve. E to the negative 3x is a decay curve. So e to the x does something like that. E to the negative 3x does it backwards. Zero, but let me show you how to find this point of intersection. Set the two equations equal to one another. Now subtracting one from the other side isn't going to help much because I can't combine them through subtraction. But I can combine them through division because they are like bases. And when you divide like bases, you subtract exponents. So instead of subtracting one from the other, I'm going to divide both sides by e to the negative 3x. And that puts a 1 over here. And like I said, I was going to subtract exponents here. So I have 1x minus a negative 3x gives me e to the 4x over here. Can you remember how to solve a exponential equation for the exponent?
Natural log.
Take the natural log of both sides. The natural log of e to the 4x is the 4x. What's the natural log of 1?
0.
So I get 4x is equal to 0, divided by 4. And it shows me that the factor x is 0. Now I want to find the area from x is negative 2 between the curves, not just between the x-axis, between the two curves. So from x is negative 2 to 0, we have that situation. And from 0 to 1, we have this situation. Between negative 2 and 0, if I put my partitioning rectangle in there, I have the decay curve on top and the growth curve on the bottom. But once I cross the point of intersection, the decay curve is on the bottom and the growth curve is on the top. And these are not spaced so that I can use symmetry. I actually have to write two different integrals. The first one from negative 2 to 0 with the decay curve minus the growth curve. And then from 0 to 1 with the growth curve minus the decay curve. So the overall area, oh, that's a bad A, is the integral from negative 2 to 0, decay curve minus growth curve. Added to the integral from 0 to 1, growth curve minus decay curve. That's the plan. Does anybody remember how to integrate, for instance, e to any number times x? What is it in general that e to, say, a number times x?
It's unknown over A, beginning, E to x.
In itself, but one over the a out front to cancel that chain rule action if you were to take the derivative. So the antiderivative of e to the x is e to the x. The antiderivative of e to the negative 3x has a negative 1/3 in front of it. So for the first integral, we will have a negative 1/3 e to the negative 3x minus e to the x as the antiderivative, evaluated from negative 2 to 0. Add to it e to the x, now minus with the other minus, will give me a plus e to the negative 3x with a 1/3 in front of it, from 0 to 1. And then the rest is blah, 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 right? When I put 0 in here, e to the 0 is how big?
1.
So when I put a 0 in here, I get negative 1/3 minus 1. Now I'm putting in the negative 2. So I get e to the 6 minus e to the negative 2 with the 1/3. Negative 1/3 in front of the e to the 6. Now I'm going to put the 1 in here, e to the 1 plus 1/3 e to the negative 3. And then the 0 is going to give me 1 plus 1/3. You can enter it just like that. X on it? Nope. X on it.
Because I did the same.
Wait. Try that, didn't do it either. So it's not working. There we go. Almost can see it all, almost. Let me do it. Numbers, we don't care about numbers. What's the next one you want me to work? 5 first, 13 second. Number 5 is asking me to do.
Enclose between 2 sine of x and 4 cosine x. Y equals this. And it's from x equals 0 to x equals pi over 2.
Okay. All right. So I'm going to draw this on the interval from 0 to pi. On the interval from 0 to pi, the sine curve is that, where this height is at 2. On the interval from 0 to pi, cosine is going to be down here at -4. And up here at +4. And then it's going to cross at pi over 2. So it's going to do some dilly like this. We want the area between. So from x is 0 to this point, we got this bit between them. Once I cross that point and go over to pi halves, I got this much. So again, we have a non-symmetric pair of regions that change top functions and bottom function as I cross the point of intersection. So we're going to do 2 integrals. We're going to find that point of intersection first. Set 2 equations equal to one another. And we will have that 2 sine x is equal to 4 cosine x. So I'm going to divide by 2 and divide by cosine. When I divide by 2, it puts 2 here. When I divide by cosine, I have the sine over the cosine. So that's going to give me a tangent. That's not one of the angles that I know as one of my reference angles. So the best I can do is say that the point of intersection is the arctangent of 2. So I'm going to integrate from 0 to the arctangent of 2, then from the arctangent of 2 to pi halves. And I'm going to put the appropriate top and bottom graphs in there. So for the first one, we've got from 0 to arctangent of 2. What's the top graph over there?
4
cosine. The bottom one is the 2 sine of x. Then I'm going to start at the arctangent of 2 and they swap. Let me get to pi halves. I'll put the 2 sine of x first, minus 4 cosine of x. That part okay? It's just the numbers they got to you. We'll make it hurt less. So you gotta tell me what happens, what do I get when I integrate cosine? What do I get? And what about when I integrate a sine? Negative cosine. Right? So that's gonna fix the negative cosine. So I'm going to get 4 sine of x plus 2 cosine of x from 0 to the arctangent of 2. And then here I get minus 2 sine of x minus 4, whoops, sorry, that's a cosine. Minus 2 cosine of x minus 4 sine of x to be evaluated from arctangent of 2 to pi halves. Everybody with me? Okay, so I'm gonna put the arctangent of 2 in there. But I'm gonna kind of do it to the side. Let's figure out what that is. We're gonna, in each of these steps, have to evaluate a sine of the arctangent of 2 and the cosine of the arctangent of 2. So I'm going to appeal to your calculus 1, where we did the review of trig and algebra in chapter 1. Inverse trig functions represent angles. So this is a particular angle that I would take the tangent of to get 2. And if I know the value of a trig function at the angle, then I know all of my trig functions at that angle. I can draw a picture. The tangent of an angle is equal to 2, describes 2 sides of a right triangle whose ratio of opposite to adjacent is 2. How big is the hypotenuse then? Square root of 5. So what is the sine of that angle?
2 over the square root of 5.
2 over the square root of 5. And the cosine would be 1 over the square root of 5, right? Opposite over hypotenuse. You guys remember doing stuff like that? Otherwise, you can just write it as a composite function, and there goes your little copy typing. Okay, but I'm going to use those numbers. So when I put that in here, I'm going to have 4 times the sine of the arctangent of 2. So 4 times 2 over root 5. Plus 2 times 1 over root 5. Now we're going to do this part in our heads. We're putting 0 in for each x. What's the sine of 0?
1. 1 times 4 is 4.
Nope, sine of 0 is not 1 though.
Oh, sorry.
0.
0.
Cosine of 0 is 1.
1, yeah.
So I'm going to get 4 times 0 plus 2 times 1, and we get 2 out of that, behind this minus sign. So far, so good? Now we're going to go again. Down here, we're going to do this part in our head. We're putting pi halves in for each x. Cosine of pi halves and the sine of pi halves. So I'm going to get minus 4 out of that. And now I'm going to get the same numbers again, except I've got these coefficients. Cosine of the arctangent of 2 will look like negative 2 times 1 over the square root of 5. And then minus 4 times 2 over the square root of 5. And that probably simplifies nicely for us. Let's see. I have 8 plus 2 gives me 10 over the square root of 5. That's another 10 over the square root of 5. Negative with that negative for a grand total of 20 over the square root of 5. Quit listening a long time ago, didn't you? Minus 2. Minus 4. gives me a -6. There's our answer. Or you can just type it in as a bunch of composite functions. I'd rather use my little finger. Yes.
Could you go back to 12? Because like while everyone had the e to the -3x, I had e to the -x, and I'm
All that's gonna do is make these into ones right here. So change every 3 into a 1.
and I could just input the thing like that, or
Yeah, make every 3 into a 1. I think I've already counted for the sign, maybe.
what I have here.
Number 7.
7? Tell me what it is, please.
The area between the graphs x plus 4y equals 17. And x plus 4 equals y squared.
Okay, so we got line and a sideways parabola. Agree? Okay. All right. So x plus 4y is equal to 17, and x plus 4 is y squared. I can draw it a little bit better if I write this as x is equal to y squared. What does the graph of x is equal to y squared look like?
Sideways.
From the origin, right? And I'm gonna move that 4 over. So it took that parabola from 0, 0, moved it back 4. So it's got its parabola opening sideways, the vertex at 0, -4. Let's say that's 0, -4, or -4, 0, sorry. It's going like that. Let's see if x is 0, that's crossing the y-axis at plus and -2. Now, this is a line that when y is 0, x is 17. So what the heck, let's put that right here. And when x is 0, y is 17 over 4, which is 4-ish. So that's going to be a I think the line goes down to there. Okay, so I missed. Big matrix full. It's 2 points of intersection that we're going to need. Okay, let's find the points of intersection. It looks probably easier to find the points of intersection if I find the y values. So I'm going to take this one and write it as x is equal to 17 minus 4y. And then I'm going to set that equation over that one. Now I'm going to get 0 on the left-hand side, move all that other stuff over. Put in descending order to get y squared plus 4y. So I'm subtracting 17 gives me a minus 21 here. I need factors of 21, opposite in sign, that add to a positive 4. So this is -3. So my 2 points of intersection are y is equal to -7 and y is equal to 3. I'm betting this one's the -7 and that one's 3. Now, Let me put -7 in here to get the x. -7 squared is 49. 49 minus 4 gives me x is 45. And now put the 3 in there, 4, 9 minus 4 is 5. We happy with that? Is this the problem that asks for you to do this 2 different ways?
Yes.
So let's set up the dx integral. What do you know about the dx integral? Like typical dx partitioning rectangle. I've got one of them that hits parabola on both sides. Once I cross that point of intersection, the top graph changes. So I'm going to use 2 integrals with a dx. And if I'm doing dx, I need to rearrange my equations so that y is a function of x. So let's see. If I take this equation, I can get the top and the bottom part of the parabola by taking the square roots. The top part of the parabola is the positive square root of x plus 4, and the bottom part is the negative square root of x plus 4. I'm going to take the equation of the line and solve it for y. So I have 4y is 17 minus x. So y is 17 minus x over 4. And as dx integrals, we get 2 of them. We're going to integrate, say, from this x to that one, from -4 to 5. Top graph minus bottom graph. Square root of x plus 4 minus a negative square root of x plus 4 will give me 2 of those. Great. Next integral begins at 5 and moves all the way out to 45. Top graph, 17 minus x over 4 minus the bottom graph was the negative square root. So minus the negative square root, we'll put a plus here. Okay. So it asks you for these numbers and this guy. These numbers and then this guy. That's what you put in the little blanks. But I don't want to do that because I can see that a dy integral, dy area can be done with one integral. To show you that, I draw a dy rectangle. And everyone hits the line on the right and the parabola on the left. So the dy integral is the easier one, and I need my equations written in terms of a variable y. Like that. So as a dy integral, I look at my smallest y value. What's the smallest y value in the region? -7. Then I integrate to the tallest y value.
3.
3. So we integrate from -7 to 3. Rightmost graph is the line. The line was 17 minus 4y. The leftmost graph was the parabola, y squared minus 4. And then you can do that one in one swoop. You can combine that first. Let's see, we have 17 minus a -4 gives me 21 minus 4y minus y squared dy. That's the one I would do if I would do it. I think I can trust you with that part. It should both give you the same number. Is that okay with you? 15?
Yeah.
That's just 13. Let me find a place I can put it. We'll put it way over here on the left board. All right, who wants to tell me what it is?
Sketch the region enclosed by 2y is equal to 4 times the square root of x, y equals 5, and 2y plus 2x is equal to 6.
All right, name, enclose a region whose area we wish to find. We just want to sketch it,
Yes, was the sketch the region enclosed.
and that's it.
Then it says decide whether to integrate with respect to x or y on the area of the region.
Oh, and then find the area. Well, okay. Well, okay. I start here. Y is equal to 5 to the horizontal line. That's another line? Okay. That's not a line. What does the graph of y is equal to the square root of x look like? Part of our parabola opening to the right. So if I divide by 2, I get y is equal to 2 times the square root of x. So y is equal to 2 times the square root of x will look something like this, just a little bit taller, right? So then we leave room for y is equal to 5. Y is equal to 5 is a horizontal line. So that's going to come through here. All right. And that is a diagonal line when y is 0, x is 3. So let's see, I'm going to make this a 5. So that's 3. And same deal when x is 0, y is 3. So that line does this. And then the line y is equal to 5 puts a top on it. The region that we're looking at is this little nearly triangular shaped region. Because we weren't given the y-axis or the x-axis as a boundary. So we're finding the area in there. Am I agree? Let's find all the points of intersection. First, let's get this one by putting 5 in for y into the equation of that line. So I'm going to take this 5 and put it here and solve for x. 3 times 5 is 10, plus 2x is 6.
Be negative
Negative 4 is equal to 2x. X is
negative 2.
negative 2. And y is 5. That's that one. Now I'm going to put y is 5 into the equation here. So I'm putting a 5 right there. 2 times 5 is 10. 10 divided by 4 is 5 halves. 5 halves is the square root of x. What is x?
So like 25 over 4.
So this has x is 25 over 4. And y is 5. And then the last point of intersection comes from these two. So I'm just going to,
You just do 4 square root of x plus 2x equals 6.
okay, I'll take the 2y out, put 4 square root of x in there. All right. So 2y plus 2x is 6, and 2y is 4 square root of x. And so I'm going to actually just subtract. So the 2 y's are out. And I have 2x is equal to 6 minus 4 square root of x. I can see the answer. Algebra is icky, but can you see that x is equal to 1 works?
Yeah.
X is 1 using the 2 here, X is 1 using the 2 there. So just by dumb luck, X is 1. Otherwise, we square both sides in combined terms. Okay, so X is 1. Otherwise, we do this. Get middle terms in. Okay, someone go X is 1. X is 1. Y is, see if X is 1. Y is 2. Okay. I'm not forced to integrate it in any particular way. Which way is the easiest? Y. Integrate dy. Because dy gives you the same boundaries all the way up the region. Okay, the right graph is that little half parabola. The left graph is the diagonal line. So a dy integral is the easiest one to do. Let's erase this and put it right here. If it's a dy integral, I got to put functions of y in the integrator. So I'm going to take these and write them as functions of y. So let's see, if I write that as a function of y, I divide by 2, and I get y over 2 is equal to the square root of x. Square both sides, so I get x is y squared over 4. That's the rightmost graph. The leftmost graph comes from this line, and I'm going to solve for x. So first I'm going to divide everything by 2 and get x plus y is 6. I'm sorry, divide everything by 2 and get x plus y is 3. So if x plus y is 3, then x is equal to 3 minus y. Are you checking my arithmetic? Or again, you're just sitting there. Your job is just to write whatever I write. So what if I just wrote a bunch of expletives up here? Would you copy them down?
Yeah. I probably take a photo of that.
You know what has happened to me? I don't even know how our fight song actually ends anymore. You guys have taught me a new ending to the Texas Tech fight song. And I said, how does it really end? Surely it doesn't end that way. Sounds pretty good there.
God bless you.
But it's embarrassing when I'm like singing it with other adults and then I come to that part.
Just don't say.
So I see, it's the same thing. I can write whatever I want up here and you choose writing.
Yeah.
It's that learning thing.
I just take a, like he said, I take a photo of it and I just post it like.
Yeah, I probably send it to a bunch of folks and be like, man, look at what my professor did.
Right, get me fired.
I would have like name dropped you.
But it's like, okay, there's only so many calculus classes that are honors calculus classes, so.
And unnamed professor and unnamed class.
Blame Nunez.
Found her. Okay, so what I said was, we're going to integrate dy. So I'm going to get y values. What's the y value that I'm going to put here? Yeah. What's the y value I'm going to put here? All right. Let's see that? Bottom y, top y. Now the rightmost y comes from this graph. And we said that graph was x is y squared over 4. Leftmost graph is this diagonal line. X is 3 minus y. So that looks like a pretty easy integral to do, doesn't it? Much more than writing 2 integrals and using numbers like that. Picture tells us everything, so you got to really hone up on your graphing skills. Be careful and make your picture big enough so that you can see it. Not really a tree shortage. You can use as much paper as you want. You come in here and write on the pretty green ones. Got any others?
Can you go over number 11?
11. Eleven says what?
Find the points at the intersection of the graph, y equals 3 sine of 6x, and y equals 0, between x equals 0 and x equals 3 pi over 12.
3 pi over 12, which I know is pi over 4.
Yeah.
I can remember this.
And then it says find the area bounded by the curves that we just stated.
Between those. Okay. What does the 6 do to the sine curve? I know the 3 does, it makes it taller.
Is it like widen
And widen it. Squishes it together. Normally the sine has a period of 2 pi where it does its little sine movement. But now it's going to do that in the interval of length 2 pi divided by 6. So this sine curve now goes between 0 and 2 pi divided by 6. So here's our sine curve. So instead of twisting that like that, that point is 2 pi over 6 or pi thirds. So if that's pi thirds, what's this one? Half of pi thirds.
power
Pi
6.
over 6. So at 0, the height of this is 3. And down here it's a negative 3. Okay, where's pi over 4 in all this? This is pi over 2 pi over 12. This is 4 pi over 12. And this is 3 pi over 12. So it's smack dab in between these two. So our 3 pi over 12 or our pi over 4 is right here. And so we draw that as a boundary line. And what we want to find from -0. No, -0 is here. X is 0 is here. From here to here to here to here. That one. Got it to that one. So we can do this with 2 integrals. Or we can cut it up into 3 chunks of equal size, find the area of 1 chunk, and then triple it.
Well, I had an issue. I found the top section in mine, but then like the bottom section, I kept getting something weird.
It's cut smack dab in half.
Yeah, well, I didn't think about that, but when I did the actual integral, I kept getting like a weird answer. I kept getting a negative.
Did you do 0 minus?
I believe so. Yeah, because I had -3 sine 6x.
And then when you integrate 3 sine of 6x, what do you get?
I got. Oh, never mind, I just found my error. Thank you.
So you get a negative cosine, don't you? Okay, but let's do that. Let's say we're going to integrate from here to here. And triple. So we have to figure out what that is, but it should be halfway between 0 and pi 6.
You already know the values change. Integrate from pi over 6 to pi over 4 and triple that.
Pi over 0. I like zeros.
So that's fair, never mind.
Whose class is it? Mine or yours?
Oh, sorry.
But the pi over, it's not gonna, you're right. You can integrate from here to here and triple it.
Less than.
I can take half of pi 6.
Remember.
Integrate from 0 to pi over 12 and triple it.
I didn't mean anything.
I'm just kidding. I like the
It's a lot
suggestions.
by you.
I want you to participate. I didn't mean to shoot you down.
That your pie was loaded.
But I like your suggestion. Just like you.
Noted.
I'm gonna integrate from 0 to pi over 12, triple it, and then we're gonna see if you guys can figure out how to do this integral. So maybe with 3, that comes a 9 out there. What happens with that?
So that changes to negative cosine.
And that?
You gotta add the 1/6 to cancel out the 6 in front.
gonna get 1/6 times a negative cosine of 6x. From 0 to pi over 12.
You could also just use a U sub, right, for the 6x.
That's, we kind of did that in our head, right? If u is 6x, then du is 6 times dx, so 1/6 du is dx. And this becomes 3 times 1/6 sine of u du. So I get a -3/2 right there. Now I'm putting pi 12s in, multiplying it by 6, and I get pi halves. What's cosine of pi halves? It's a nice round number. Now I'm putting 0 in there and I get the cosine of 0. It's not a round number. So together I get -3/2 times -1. The grand total area is a positive 3/2. Okay. So that was a good problem so that you could remember that you use substitution, the opportunity to use some version of symmetry, and how to graph your trig functions. Hold on to it. That was web work, or do you have more? I did like 8 of them. So how do you feel about the length of the homework?
It's reasonable, for sure.
Reasonable? Is it redundant? Is too redundant for you?
Nah.
I made this one longer just to get you a chance to review your integration techniques. I tried to slip in different types of functions to integrate. So I put the trig, I put the e
Pretty solid.
in there to get you to practice.
I like that.
That's important. I'm here to make you happy. Somewhere in there, put a little education in you. Anything else? Okay, we were talking about finding volumes and we were looking at volumes by slicing. And I said we break it up as essentially looking at the area that the cross section gives us, multiplied by the thickness, which was going to be our dx, integrate that over that two-dimensional region, and we have volume, area times thickness. And cross sections were usually some sort of circle or semicircle, so pi r squared, or a square, which have areas side squared, or an equilateral triangle. What was the area of an equilateral triangle as a function of the length of the side? Remember we wrote the altitude as a function of the side?
Square root of 3/4 s squared.
Right, 3 or 4. So I'm gonna rub that out and I'm gonna write all that down. Like this. Example would be what? It's hard to erase today.
Where are you so lost on?
There's a bird somewhere in the ceiling in my office. And it's been there for 2 days and it's starting to really cry.
Oh.
So you get extra credit if you'll crawl up there and save it. I'll do it.
Extra credit?
I mean,
I'll do it.
I had a man yesterday with a net and he
If I
couldn't
get
catch it.
then I don't care.
Well, you know, how do I explain that to your relatives? She needed 5 points.
What kind of bird is it?
It looks like a pigeon.
I've had like the
Grades are
lifelong
grades.
goal of catching a pigeon here. So.
Yeah, so you can see if it's a robot or not.
No, it's just because like the pigeons here seem so catchable.
Is it?
Yeah, they're so fat and stupid.
I am so tempted to pick one up and go see you.
Yeah, right. I'm glad I'm not the only one like that.
Hold on,
Walk up to them until we like actually walk
Yeah,
up on them and then they fly.
Is it a better idea to leave it in the ceiling flapping and?
Well, I mean, once it
Or
dies.
should I remove a panel and let it escape to my office? Which is better for
In your
the?
office,
I'm
then.
gonna fire
Well,
it.
if it dies in there, it's gonna smell awful, so I'd say let it loose.
Plus, you-
Or you just let it die.
After it picks my eyes out.
That spells Dave. That spelled, that's
Really?
really good.
Hey, if it dies,
I can see that bird now. You witch, why did it take you 2 days to let me out? I tried. Okay, 6.2. So the first one was solids. Known cross section. So the idea was that we look at our slice. We've got some sort of region in the XY plane. We're told that when we make a slice like that and pull it out, it has some sort of shape. So the solid's out of here. You slice the solid, pull that piece out, turn it around, and you recognize the shape. And so the volume was going to be whatever the area of that shape is as a function of x times its thickness. That's the dx. And then we sum that up from x is equal to a to x is equal to b. If we're told that the cross section is a square, then for area, we just use s squared. Where s would be top graph minus bottom graph. If we're told we have a semicircle, then area is equal to 1/2 of pi r squared. S would be the diameter of that semicircle, so r is going to be half of s. If we're told that our cross section is a square, we already did that one. How about an equilateral triangle? Then our area formula is square root of 3/4 times s squared. Again, s is top graph minus bottom graph. So the only adjustment we have to make is what the general formula looks for and whether we use top graph minus bottom graph or half top graph minus bottom graph. We're talking about a radius. Okay? And so there's really nothing to decide because you're told what the cross section looks like. Nothing changes if we go dy other than all of the Stokes functions of y. And so, how many of these did we work last time? A whole boatload of them?
You need three.
Three?
You got through A, B, and C on one.
With B and C of one?
A and B, C.
Oh, so do you have another?
There's a second one.
Okay, well, let's look at the second one then.
Oh, yeah, the second one's semicircles.
Okay. Know what they're talking about. You got one?
Blackboard?
It should be, but here's one on paper. Anybody else need one on paper? Lick my fingers and spread all this like particles to you. Wait, that's correct. It's the second page of that. Come on, paper. Else? So the second one says, with the graphs of y is equal to, what does it say, x cubed? And y is equal to x, and those two bound a region. So draw me those two graphs, y is equal to x cubed and y is equal to x. Those bound a region in the XY plane. That looks something like this. Limit y is equal to. We'll put a top on it. And I want the first quadrant. So it's that little banana shape there. There's a solid whose imprint on the XY plane looks like that. And it's coming out here in such a way that if we make cuts perpendicular to the x-axis throughout this region, that thing comes out and looks like a semicircle. We've got semicircles coming out here. And another one coming out there, another one coming out there, and so on. Okay. So that gives me that. Where this is S. And so we've got semicircles. Which tells me that the area is 1/2 pi r squared. And r is equal to half of this. Great. What are you going to write as S? See what S looks like. X minus x cubed. We clearly intersecting x is 0. What is the other point of intersection? X is 1, right? 1 is the same as 1 cubed. So our plan was that volume is equal to the integral of 1/2 pi r squared dx. We just said r was x minus x cubed over 2. And that the x's vary on this region from x is 0 to 1. Right? So there's my plan. There's me doing it. 1/2 pi r squared dx. You see how we need to do the rest of the integral? What do we have to do next?
I pull out pi over 4, or wait, actually 1/2 pi for the meantime.
Okay.
And
That can go out.
and then we start expanding x minus x cubed over
And
2.
that's gonna be a 4, right? So go ahead and pull out pi over here. Let's be good.
Oh yeah, it's good.
Pull out pi over 8. Now we got to take x minus x cubed and square it. So that's it to square the individual terms. Don't be lazy on me. Let's square it by multiplying it out. So I'm going to get an x times x will give me an x squared. My middle terms will be duplicated. My middle term is going to be a negative x to the 4th, so I've got 2 of those. And then a negative times a negative gives me a positive. Remember how to multiply x cubed with x cubed? What do you get? X to the 6, you add x on it. And the rest is easy. And by termination, x cubed over 3 minus 2x to the 5th over 5 plus x to the 7th over 7. With zeros in there, all of those are 0. When 1 is in there, all of those x's to a power will become 1s. So our total volume is pi over 8 times 1/3 minus 2/5 plus 1/7. Fast? There's another problem written on a tiny piece of paper. Let's see if it survived. Nope, it did not. I'll read it and then I'll write it. The base of a solid is a triangular region with vertices at 0, 0, 3, 0, and 0, 2. Make you a triangle with vertices at 0, 0, 3, 0, and 0, 2. Now you're told that cross sections perpendicular to the y-axis semicircles. Find the volume of the solid. That's not quite a volume. Let's at least set up the interval that finds its volume. Let's see what kind of adjustments we need to make when we go perpendicular to the y-axis. I don't think there's any big time drama. I'll let you think about it. Here's 0, 0. There is 0, 2. There's 3, 0. Here's our triangle. Cross sections perpendicular to the y-axis. Come out like that. Give us semicircles. There's our little dy, I suppose. So I'm going to write this again, but I'm going to write that as a function of y and a dy there. Where this is going to be 1/2 pi r squared. And how are you going to find r? R is s. R is s. How do you find how long s is? How do you find how long the box is when you've got a horizontally simple region? Right line is left. We need the equation of the right graph. I got the equation of the left graph. That's x is 0. Now it's your turn. I need the equation of the right graph. And write it as x is equal to some function of y. You can start by writing it as a function of x and then rearrange it. Because I've got a line, slope is something, its y-intercept is 2.
Would be x equals -3 minus y.
Okay, let me see. M would be 2 minus 0 over 0 minus 3. So M looks to me like a -2/3 x. Y-intercept is 2.
Never mind. Got the 2.
So I gotta move the 2 over. And then I gotta divide by that number. Divide by that number gives me a -3/2 here. And then you can send out through the parentheses. And I think what you said was right. -3/2 y is running into my problem.
There's the 2 on there. Slope was good.
All right. So when I distribute that, I get +3. And that's gonna be our s, because my left boundary is x is 0. So that is s. And I said I need to use 1/2 s right here, just like we did in the last example. So that's s. R is equal to 1/2 of -3/2 y plus 3. And volume is equal to the integral of 1/2 pi r squared dy. So think goes like r. What happens on the integral sign? We got any numbers for me for the integral sign? How much? On this guy. From 0 to 2? Right?
Yeah.
All right, the rest is algebra, so we skip that and stop right there. But again, you have to square that and expand it all out and just be careful, careful, careful. Okay? So there isn't any reason to go into the dy realm. It doesn't look any different than the dx realm. So we won't. I just did that just because we were probably curious.
That's what I'm pretty sure probably gonna be questions on the homework about this.
No, I didn't put any dy's on the. No, I didn't put much. Again, that's what we're curious. One thing you make sure is all your variables are free and these numbers are variables. And none of the numbers change. Okay, so the next one in this section, we are going to take a region in the XY plane bounded by some graphs, and we are going to revolve that region. And as that region revolves, it's going to generate a three-dimensional solid. And we're going to find the volume of that solid. So that part 2 will be called volumes of solids of revolution. So the first type will do something like this. We'll have a graph. Maybe a y is equal to f of x. And the x-axis bounded between two vertical lines. Take that little region there. And let's revolve it about the x-axis. So that same shape comes out here, goes back into the board, and it makes a three-dimensional solid with curvy sides. It's not some solid that I know from geometry, a volume. I can take a similar version, x is some function of y, bounded between y is equal to c and y is equal to d, and revolve it around the y-axis. So in either case, the boundary line serves as the axis of revolution. If the boundary line serves as the axis of revolution, my plan is my run-of-the-mill plan in calculus. I'm going to take my region and cut it up into little bitty rectangles. That's all we're going to do all semester. Take a region, cut it into rectangles. So I'm going to take this region and I'm going to cut it up into little rectangles. And there's one of them. And I don't care what the region looks like that I'm revolving. I want to know what shape is generated when I revolve that rectangle. Take that one rectangle that's infinitely thin and revolve it here about the x-axis.
That'd be a circle.
It's going to be a circular disc. So I can find the volume of that one circular disc. It's the area of that face, pi r squared, times how thick it is. If I partition in the y direction, same deal happens. If one of the boundary lines of the region is the axis of revolution, swing that rectangle around, and I again have a circular disc. Pi r squared times the thickness. In this case, the thickness is going to be a delta y. Here, the thickness is a delta x. I find the volume for each of those rectangles, I put it in a Riemann sum, I take the limit as the number of rectangles goes to infinity, and I get an integral. So my integral will be a sum of, so we're gonna make an infinite sum of these disks. Here, I would have pi r squared times dx in my integral. And here, I would have pi r squared times dy in my integral. And r, if this thing is revolving about the x-axis, then r is just this length right here. Right? If that's revolving, then it's gonna come down here and make another little portion so that I can have my top graph minus my bottom graph as being my r. And here, I would write that as a function of y. R is going to be formed here. So it's gonna be right graph minus left graph to give me r. Okay, so that's my plan in those cases. If by chance the boundary line is not one of the axes of revolution, not much difference, things happen. Give me XY plane. Let's go with a top graph of y is equal to f of x and a bottom graph of y is equal to g of x, bounded between two vertical lines. So I'm looking at this little flag-shaped region here, and I'm going to revolve in this first example about the x-axis. If I have that version, I just stick in another graph over here. Let's say that this is the right function as a function of y, and this is the left function as a function of y, bounded between two horizontal lines, C to D, and revolve about that. Put our little rectangle in there. I think I'm out of purple ink, so let's try blue. What shape is generated when this blue rectangle is revolved about the y-axis?
Donut.
A donut? All right, so we'll draw that down here. That's gonna come out. Come out, it's a pretty flat donut, but it's a donut.
So it's like a CD.
Like a CD, you're going back into my day. It's going to be called a washer. To find the volume of the washer, I pretend it doesn't have a hole in it. And I find the volume of the disk, pi r squared. Then I pretend it does have a hole in it. So I subtract out the pi r squared of this hole. So I'm gonna know what makes each of these radii. Let's see. One radius, one around the axis, x-axis, so that's gonna be my axis of revolution. That's going to generate a big circle, so I'm gonna call that radius big R. And then this little circle that's here is whatever the bottom graph is, and it's gonna be little r. And so again, I make the whole thing as if it were a solid disk, and I have a pi times big R squared. Now, take off the circle, pi times little r squared. That gives me the area of the cross section times the thickness to get volume. From here, we're going to have integrals that look like pi times big R squared minus pi times little r squared times, in this case, the thickness of dx then I go across the x-axis. Nothing changes here other than my washer comes out this way, back into the board, and then this makes a circle. So I'm gonna have a big circle minus a little circle times the thickness of dy. So this time, big R is measured from the y-axis to the rightmost graph. And little r is measured from the y-axis to the closer graph. But the plan's the same. I'm going to have the volume is equal to the integral, this time from C to D of the y-axis, pi times big R squared minus pi times little r squared, this time times dy. Big R and little r depend on distances of the graphs from the axis of revolution. The x-axis and the y-axis are nothing magical. I can rotate around different horizontal or vertical axes, but I'll have to compute distances. All right, now that's the plan. Let's implement the plan on our examples, which I have printed out for you. Oh, so it's not at a goofy angle. Move it back. The angle. Can we get out of here like in 2 minutes? Do you want to hear another bird story?
Yeah.
I guess I don't have time to do another one. That's the plan next time. One thing I want you to pay attention to what we're doing here in this first part. When I partition the region, look at that, how the partitioning region compares to the axis of revolution. In both examples, the partitioning element is perpendicular to the axis of revolution. The partitioning element is perpendicular to the axis of revolution. In those cases, you'll always get either a solid disk or a washer. Also do the same types of things with partition regions parallel to the axis of revolution, and we'll get a different shape. So perpendicular partitions give you a disk or a washer, pi r squared dx dy. All right, so I know we get you started, but that's enough to read today. Let's just go listen to the pitiful cries of a sad bird for another couple hours. Where's my mouse? Here.
Very nice.
So it's like a 2 minute.
Bistro that.